Welcome to that of the UG students. Now we are going to that of the JAM question solution 2024. The problem regarding the Hofmann rearrangement. The problem given that the amides that are react with that of the bromine in aqueous stage followed by aqueous HCl produces the alpha phenyl acetaldehyde. The mechanism for the synthesis of this reaction is that the at first NH bromide is formed, that is the N-bromide amides, and then this N-bromide after the Hofmann rearrangement produces the alkyl isocyanate intermediate, and the alkyl isocyanate intermediate has the phenylic part, so the phenyl amine is formed, and this phenyl amine undergoes isomerization reaction in the presence of the H3O plus produces the imine intermediate, and then this imine intermediate leaving the ammonia to produces the alpha phenyl acetaldehyde. The similar problem for that of Hofmann rearrangement is that these problems mainly coming from that of the different examinations, UG board examinations. Here the succinamides in presence of the bromine and KOH produces the beta alanine as the product via the Hofmann rearrangement. Similarly, the phthalic anhydride in presence of the ammonia produces the phthalimides, and after Hofmann rearrangement it produces the anthranylic acid. Now the problem is that of the Wolff rearrangement and the Grignard reaction. The conversion from that of the cyclopentyl derivative to that of the cyclopentyl carboxylic acid derivative, where the reaction can take place in the first option A. In the paratoluene sulfonyl chloride react with that of the primary alcohol produces the OTS, and this OTS react with that of the potassium iodide under SN2 reaction produces the alkyl iodide, and then this alkyl iodide on react with that of the Grignard reagent followed by the carbon dioxide quenching, it produces the carboxylic acid derivative, and these are the desired product. Similarly, in option B, the paratoluene sulfate, that is sulfonyl chloride react with that of the alcohol produces the OTS, and it can react with that of the potassium cyanide and followed by hydrolysis produces the carboxylic acid. That is the option A and B is also the correct option. And in the option C, the chromic acid followed by sulfuric acid, the alcohol is converted to that of the carboxylic acid, which on treatment with that of the SOCl2 and followed by diazomethane coupling reaction, and then the Wolff rearrangement produces the carboxylic acid derivative. And option C is also matches to that of the final product, but the option D is not matches with that of the final product. Here the after oxidation the esterification take place in presence of the diazomethane. So the option A, B and C is the correct. Now the problem related to that of the Grignard reaction, the problem giving that the compound which on reaction with methyl magnesium bromide followed by treatment with aqueous ammonium chloride produce 1-methyl 1-phenyl ethanol as the major product. The structure of the 1-phenyl 1-methyl ethanol is that this is the structure where the 1-phenyl 1-methyl ethanol can be formed by the Grignard reaction. The starting material is that the methyl benzoate. This is the methyl benzoate starting material, which on react with that of the Grignard reagent produces the 1-methyl 1-phenyl ethanol. The mechanism is that the reaction react with that of the methyl magnesium bromide produces the Grignard reagent, and then followed by hydrolysis it produces the alpha phenyl 1-phenyl 1-methyl ethanol. Similarly, phenyl acetate is also react with that of the methyl magnesium halide produces the 1-methyl 1-phenyl ethanol, but acetaldehyde cannot produces this the desired product, and the acetophenone can also produces the 1-phenyl 1-methyl ethanol. So the option is that the methyl benzoate and phenyl acetate and acetophenone are the correct option. That is the option A, B and D are the correct option. Now the problem is that among the following compound which produces the same oxygen as obtained in D-glucose when reacted with phenyl hydrazine. We know that the D-glucose is the C2 epimer of the D-mannose and the ketose form of the D-glucose is the D-fructose, where the configuration at the C2 position is different. Here the D-glucose, the configuration in C2 position is HOH, but in D-fructose the configuration of the C2 position is ketose. That is the D-glucose, the ketose form of the D-glucose is D-fructose. And we know that after oxygen formation, the two chiral center has been vanished, so it produces the same oxygen derivative, that is D-glucose, and D-fructose gives the same oxygen derivatives. Similarly, the D-talose, the option is that D-talose. D-talose is not produces the same oxygen derivative as the configuration at the C3, C4 and C5 are different, so it does not give the same oxygen derivative. Similarly, the CH2OH group, that is the option D, they contain the CH2OH and CH2OH group, so it cannot isomerize to the oxygen derivative as it does not have any aldehyde or ketone functionality, so the imine formation does not take place. So the option D is wrong and the option C is also wrong. The correct option is that the A and B. This is the problem related to that of the stereochemistry, where some structures are given where the compound A does not have any symmetry, so it is optically active. The primary condition for the optical activity of any compound is that the molecule does not have any symmetry except CN symmetry. That is, it must avoid sigma, I and SN symmetry, and then the molecule becomes optically active. In the option A, compound is optically active as it does not have any symmetry, so it is optically active. But in the option B, the compound has I symmetry, that is the I is equivalent to S2 symmetry, that is the chlorine. If we extrapolate from that chlorine to another chlorine, then extrapolate to methyl to another methyl, extrapolate to hydrogen to another hydrogen, then equivalent point is achieved from that of the center. So it has I symmetry. So I symmetry means it is optically inactive. In case of the C option, the molecule is optically inactive as it has plane of symmetry. If the molecule is equally halved, that is the plane is drawn from that of the intermediate between the 1 and 4 center, we get the sigma symmetry, so it is optically inactive. In case of the alene substituted derivative, here the molecule has C2 symmetry. We know that the CN is not the essential criteria for measurement of the optical inactivity, so it has C2 symmetry. It is the dissymmetric molecule, but it is optically active. This problem is come from that of the NMR. From that of NMR, how many signals has been achieved from that of molecules? If we marking the molecules, that is here the C2 symmetry is present. That is the HA and HA. All these HA are related to the C2 symmetry. That is the homotopic in nature. So it gives the one signal, and the methoxy proton of the molecules give the another signal, and these methoxy proton and these methoxy proton are same. So these methoxy are homotopic and the HA are homotopic. So we get that of the two signal in the NMR spectroscopy. In this problem, the stereochemistry related problem. In this stereochemistry related problem, after the hydrogenation of this molecule produces the two stereo center, and this two stereo center is equivalent. That is, it is the propyl group, and not it is the propyl group, not the ethyl. And this propyl group has the equivalent. So the methyl group either come to that of the same sites, or the methyl group come to that of the opposite sides. If the methyl group in the opposite side, then it becomes optically active, and so this molecule has two optically active isomer and one optically inactive isomer. So total 3 isomers are possible in these molecules after hydrogenation. A reaction of 10.50 of 1,2-diphenyl ethane 1,2-dione. This is the yield calculation mechanism, and here the yield calculation mechanism where the molecule must be converted to that of the mole. The starting material of the reaction is that 10.5 gram. If we convert it, then it becomes 0.05 mole, and after rearrangement it produces the benzylic acid rearrangement via the phenyl migration in presence of the NOH, and produces the benzylic acid, and these benzylic acids produces the 8.55 gram. It converted to that of the mole and 0.037 mole. So after percentage conversion, it produces the 74% of the product. This is the problem to that of the enantiomeric excess, percentage of enantiomeric excess, where the specific rotation of optically pure compound is 75.3 at 20 degrees centigrade. A synthetic sample, same compound, shows specific rotation plus 66.3 degree. Means it is the synthetic compound, it contains the mixture of the plus minus isomer. And we know that the formula, the percentage of enantiomeric excess is equal to specific rotation of the synthetic sample by specific rotation of pure compound. The given problem has that specific rotation of the synthetic compound is 66.3 and the specific rotation of the pure compound is 75.3, and after the division, the divided through percentage conversion, it converted to 88%. So the answer is that 88% optical purity of this enantiomeric excess compound. Thank you for watching this video. This is the last problem coming from that of the 2024 JAM solution. Next we are see that of the NET question solution 2024 for the next video.